So I want to talk about neutrino alerts from an agnostic perspective. I'm a member of IceCube, so that you know where my biases may be coming from, but the idea is to cover everybody. So why are we here is the idea that we can also provide a different view into some of the transient objects that exist in the universe. There's a wide range of things that happen that go boom in the sky. And every now and then we think that we see something that could have some hadronic component to it. And that could be related to the production of neutrinos, and therefore we want to detect those neutrinos, or use it the other way around, detect neutrinos, and then try to trigger follow-up observations that can reveal those emitters, right? From just this collection of objects, you may imagine that the range of things that we may be looking at is pretty wide, and that means also that the alerts that we may be producing, we don't really know the timescales, or at least the timescales are really undetermined. It could be things that happen in seconds, like gamma ray bursts. It could be things like happen over months or more, like a very long flare from an active galactic nucleus. So that's the kind of challenges that we have in trying to produce neutrino alerts that can be ingested by the astronomical community. But in general, whenever you have a neutrino telescope of the types that we're discussing, the high energy ones, we have different types of events that, I mean, I'm also, of course, using IceCube for this, but I'm sorry, but they really divide in two different types. There's neutrino tracks, muon tracks that are elongated, and therefore they're good at pointing. For this kind of things, we mostly want to do astronomy. We suffer a little bit in terms of the energy resolution of these events, but let's say that if we assume that the energy is high enough, we can think that those may be astrophysical in origin, because the backgrounds that produce neutrinos are low at high energies. But in principle, we have something that points well in the sky. And for neutrino astronomy, point well good means anything below 1 degree, which sounds horrible for astronomers in the room, but I was just presented, but there was a presentation from LIGO, which talks about 10,000 of the square degree. So we're good there. Then the other one, of course, is cascades that are even worse at pointing, anything between 1 and 10 degrees in the sky, or even more. But the good thing about them is that there are not that many things in the atmosphere that can produce a cascade of this type. So we may be able to look more into parts of the sky that are dominated by backgrounds if we just concentrate on the cascade events. Okay, so those are the two main things that we took away from the types of alerts that we put out. So what are the challenges really? I mean, we really have an astrophysical neutrino flux that we have detected, right? So that's a very important key aspect, right? We know that there are astrophysical neutrinos out there. But really in the astronomical community, we're like a neutrino astronomical community, we're living in these two regimes. What you see here, this very steeply falling power law, is the background due to atmospheric neutrinos, okay? And sticking away from that power law, you have the harder astrophysical neutrinos. This is kind of a dated plot, but for practical purposes, what matters here is that below some energy of about 100 TeV or so, we're dominated by background. So we can look for neutrinos that are coming from an astrophysical source, but only by correlating it in time or space with other neutrinos, because we'll be completely swamped in background, okay? So what we do there in the kind of low energy regime, where we're dominated by neutrinos too, but of atmospheric origin, or perhaps muons that pass our cuts, is to look for correlations in the sky maps, or to look for hotspots near known sources of electromagnetic radiation, or to look for hotspots near gravitational wave events. So in that way, we can try to find some alerts that we can send out to the community. That is very hard. So the other possibilities, of course, you go to this part where your background is not so high, but therefore your flux may be high. So in the high energy regime, we're signal dominated, but at the cost of having a very low event rate. At energies above 10, or let's say 100 TeV, your rate across the sky is about of order of tens of events per year for a detector that is 1 kilometer cube. Okay, so it's very hard to do astronomy with 10 counts across the sky per year, but the idea is that if you send out those alerts to the community, they may actually point a telescope of some kind and be able to detect something going on in those locations. And that's illustrated here with IceCube track alerts, but it could be any kind of a neutrino alert produced by one of the existing telescopes. Okay, so talking about 16 telescopes, these are really the three main ones in operation right now. When I said orders of tens of neutrino events per year per cubic kilometer, it's because most of the neutrino telescopes are trying to either add the kilometer cube or trying to aim for a size of about 1 kilometer cube. The first one, IceCube here, actually became operational in 2010 with a 1 kilometer cube already. But there are more lines that are not going to increase that much the actual size of IceCube, but are going to let us understand a bit more of the ice, maybe do some GeV neutrino astronomy. But really, the other telescopes that are currently in operation, either in the Mediterranean Sea or Lake Baikal, are trying to aim that 1 kilometer cube figure, right? We have about a quarter of the way, there's like KN3net built. There's also Baikal GVD that is about 60% done, about 0.6 kilometers cube, with different challenges, different technologies, and so on. But still, all of them are trying to reach that 1 kilometer cube. Okay, so there are future ones that I'm not going to mention that much, but I will mention perhaps briefly because it will become important in the next decade. So what are these telescopes sending to the community right now? So IceCube sends alerts starting in 2016. Then it went through a revision in 2019 and again last year, where IceCube sends to just the astronomical community publicly the positions of neutrino tracks that were detected by IceCube. And since 2019, this selection has led to these two alert streams, the bronze alerts and the gold alerts, that each have like 30% average or 50% average for physical probability. Okay, so not super pure, but still much better than just like the background that we get. These events are circulated to the community via GCN notices on Kafka, and the delay between the detection at the pole and the actual circulation to community is at the level of 30 seconds or so, so very fast. And on top of that, at a rate of about 8 a year, we have these cascades, right? You see kind of the hill peaks map associated with one of these cascades. The localization is not that good, but the good thing about them is that the astrophysical probability is higher. And also, they actually come out with a map associated to them. So actually, IceCube has been producing this for a while. So have there been any changes to IceCube recently? And the answer is yes. In 2024, a new way to analyze the IceCube events went online, trying to benefit from two different approaches of event reconstruction called millipeak Wilks and spline MPE with this likelihood scans. It was realized that you could get a better localization of your neutrino events by a factor of 5 or so if you try to select them in some way and then circulate the localization after you use these particular reconstructions. So starting in 2024, there has been a revision to the algorithms that are used to reconstruct the events. And that means also that we now have an archival data set of better reconstructed alerts. And I'm not going to say anything about that because Angela is going to be talking about that tomorrow. Okay, so that's one. The main thing that's happened for IceCube perhaps is this update to the reconstruction to get a factor of 5 improvement in the uncertainty of the positions of the neutrinos. The other thing that is coming online soon, hopefully by the end of the year, is that, okay, those are single neutrinos that are sent out to the community, but we can also look for clusters of neutrino events. And that is done in this way where there's an MOU between Cherenkov telescopes and IceCube, in this case, where you look for clusters of neutrinos around known sources. And whenever there is a cluster that pops up, you tell the ICT, please observe this source because something is going on there. And that's been going for a long time, but now the idea is to revise that source list. And instead of having it privately done through an MOU, you can actually share this with the community. So with a much broader catalog of sources that gets information from the KV, from GV, and from TeV, you can actually look for clusters around known sources. And whenever one of them crosses a particular significance threshold, you can tell the community, hey, there's something going on near the source. Maybe take a look to see if it's doing something weird, okay? Now, KN3net is becoming operational. As I showed before, they have about 25%, I think, of the strings in the water. And one of the big promises of KN3net becoming operational for alerts is that there's less scattering of light in water. And what that means is the actual angular reconstruction in KN3net should be better than in ice. And that has been shown recently at the ICRC conference. with this kind of projections for the angular resolution, you see that energies of about 10 TeV or so, you're at the level of a few tenths of a degree already for tracks in K3net. So your probability of correlating something with a neutrino goes with the PSF squared, right? You make the radius of your uncertainty region smaller by a factor of 2, the solid angle that you're covering in the sky goes down by a factor of 4. So whenever you gain a factor of 2 in angular resolution, you gain a factor of 4 in your chance probability of associations. So that's going to be very important in the near future. What's been happening also in K3net, they've been doing this whole revision of how they're going to actually submit alerts to the community. They have this very complicated thing. I'm not in K3net, but I'm pointing you to the proceedings of the ICRC conference if you want to read more about them. But the idea is that they're going to combine not only the selection of the events, but they're also going to look a lot into what kind of counterparts are near that event. So they will provide you with the event information, but also potential counterparts in the area. The hope is that by the end of this year, they will have these alerts being sent out publicly like IceCube does right now. And that's, I think, understand is in the works. The other big neutrino telescope that is being built is Paris-Saclay. Fortunately, I tried to reach out to the authors of the ICRC conference proceeding. I couldn't get a response, but the idea there is that so far they've been concentrating so far on the calibration and the reconstruction of the events from Paris-Saclay. So while they're not sending alerts out yet, they've been following alerts from other instruments. For instance, from this potential correlation between an IceCube neutrino and a blazar, they tried to look for additional events, and they found one kind of in close position to this blazar PKSO 735. And they also been trying to do some follow-ups of gravitational wave events. So far, Paris-Saclay is concentrating more on the follow-up of other alerts rather than on the production of alerts themselves. But this is going to be much more interesting in the near future, or perhaps not so near future, especially like you're getting kind of towards or even past your mid-career, like myself, I guess. It's for the younger people in the audience, going into the 2040s even. You may have instruments that are going to be built in the Pacific Sea off the coast of China. Trident, Hunt, and Neon are going to be 3 instruments that are being proposed in that region. In the southern part, for the South Pole, IceCube is going to build into IceCube 2. That's going to improve the size of IceCube by a factor of 6, perhaps. The construction of K3net, and of course, like in the northern hemisphere, also the full construction of P1. So all of these instruments are going to improve by a lot. Sorry, yes, thank you. Our ability to reconstruct neutrino trajectories. So I'm going to go very quickly through this. Apologies for that. But if we're having a lot of neutrinos, a good thing will be to try to combine all of them. And since neutrino telescopes are located at distinct places on the Earth, they actually have distinct characteristics of where they look in the sky and what their sensitivities are. So something that is at the South Pole can see more sensitively into the northern sky. And you can combine the sensitivities to get something that looks like a global neutrino telescope. And that can improve your rate of detections by a factor of 10 or up to 30, depending on how much you buy into this thing and how many telescopes you have operational in the near future. Of course, this is all going to happen in a very rich landscape that is quickly evolving. Not only do we have the neutrinos that are being sent out, but also we need the electromagnetic or gravitational wave capabilities to follow them up, right? So I'm not going to go into the detail of this really long table because it's a great review paper from a few years ago, but still really, really good that you can look at. But we need eyes in the sky, right? Thank you. We need eyes in the sky. People here are in SVOM, SWIFT, but we need to be covering a very broad range of wavelengths if we want to find the potential counterparts of neutrinos, going all the way from KeV, MeV, and finally the TeV range, right? So we have new telescopes, some that have been operational for years and some that become operational in the near decades. So what we really need is to have all of these tools being fed into these brokers that we have right now, tools like, of course, Astro-COLIBRI, where we can look for transients and correlations with things that are happening in real time that can also help us plan for observations. So I'm going to leave you with my wish list. Of course, we want more neutrino alerts. We want to have much better coverage of the entire sky in electromagnetic waves, but we really need better ways to integrate with the electromagnetic community and to use tools to be able to bring all that data together for users to continue discoveries. So with that, I think I'll thank you for